We have time for maybe 2 more questions, the broader session, not just to Umberto, to Dan and Julie as well. Dan?
My question is to Addie, actually. So your coefficient of restitution and the physics that you presented indicate that, is Addie actually here?
Yeah, she's back there.
Okay.
Julie? This is Julie.
Oh, actually, yeah, Julie, sorry.
It's a shame you never talk in your own department.
I suppose not.
You're never there.
It's, well, for the last 2 months, that's been true.
We figured it out back there, and we were like, probably Julie. Okay, let's go.
Okay. Anyway, the physics that you're showing is really interesting, and I think one of the implications for the bounces that we saw on 67P from the Philly lander, a lot of people have been suggesting, well, you know, comet material is a lot stronger, and there's lots of ice close to the surface, and I think the implication is that that doesn't necessarily need to be the case.
So I agree. So I've seen, actually, right after it happened, I've seen presentations that were saying, you know, we only see embedding when we do experiments, so we must have hit a hard surface. But I don't agree with that. Actually, you only see embedding at lunar level gravities, and then if you go to the small body gravity levels, which is under 10 to the minus 4, like 10 to the minus 5G, which is expected at like Bennu or Ryugu, you see bouncing just because the regolith grains like each other more. And so they will react in a very different way. And so this might be a very standard response of a regolith soil on a small body.
Something that the Hayabusa folks are going to have to worry about.
Yes. On anyone going to poke the surface of an asteroid, yeah.
Very cool.
Okay, I have a question for Dan. And I know it's preliminary times for these studies where you did the vacuum and you saw the dehydration effect, but were you surprised that it was only a 50-degree roughly change, and what are your plans going forward for that?
Actually, I thought it would be bigger, and but you know, that's reality. The plans going forward was that we're going to try to essentially extract a sample from each one of those phase change regions and do XRD and look at how the crystal structure and mineralogy changes with those phase changes, for instance, and you know, nail down what's happening within the mineral. We actually are doing chronstatite this month in the vacuum, in the high vacuum, and it might be that is more susceptible to dehydration than the magnesium serpentines, because in general these magnesium-rich minerals are tougher than the iron-rich minerals.
Actually, I think Tim had a question.
I was going to ask if you use XRD stuff.
Okay, great.
Yes.
Dan, would you explain your water abundance in primitive objects in the solar system plot? Because you went through it very quickly. You blame poor Botke on why he doesn't know it, but I didn't understand it. I didn't even know what your axes were. Would you go back to it?
We don't really have time because it's technically the break, but I would encourage you to talk in your department.
Well, we never see each other there.
Well, you're about to be in Tucson for like 16 months for OREX operations, so. Oh, all right. Do we have, I think Akbar had a question back there.
Yeah, related to the 0.7 micron feature, do you notice like the features removed? The 0.7 micron feature, do you notice that feature is removed on the older terrain? Is that weathered away on these water-rich C and B types? You notice any correlation with that?
Are you asking me?
Yeah, the spectral folks.
Okay.
Yeah.
Dan, do you know what the spectra of the CMs I don't know, I don't have expertise on the laboratory spectrum.
Yes, as a matter of fact, I think you will find the 0.7 micron feature in every CM2 carbonaceous chondrite I've ever seen out of a lab. Not in all samples of them, of the individual meteorites, but in every one that I've ever seen, I've always seen a sample with the 0.7 micron feature, which is just an Fe2 plus to Fe3 plus transition in oxidized iron in a phyllosilicate from terrestrial samples.
And is that feature removed under thermal alteration, or?
That is a question for Dan for the slow thermal heating. Taki Hiroi did a work where he increased the temperature, and yes, as the object metamorphosed and got more processed, yes, it did go away. And I think that might have been what you were looking at in one of those samples.
Tavis's stuff, but yeah, I seem to recall that you lose the.
You do lose it. You lose it immediately. As soon as he started heating it, he lost it. One other example that I know of where it was heated by impact and released lost the 3 micron feature and only distorted the 0.7 micron feature. So it's not lost under all different types of what I would consider dehydration or heating, but the general heating process that was started by Hiroi back in the 90s did cause a loss.
After this, we're going to transition to the next group.
Umberto, can you say a little bit more about what you think causes the bluing with age?
No idea.
Okay.
Observational, and where, actually Dan may have ideas on what's going on with the components, but no, mine is.
There's the data. Okay.
Well, I guess the question is what causes the reddening to begin with? And that goes away, and then you have bluing. I think I don't know either right now.
If I have to guess, I think it has to do with temperature.
All right, let's thank all our speakers.